I maker stanno andando.
So makers are going to Rome with serious, useful, but also less serious inventions. Let us now speak about space. Let's speak about Mars with a speaker that's come here from NASA. He's a NASA engineer. He's the head of navigation. Actually, he used to be, the speaker corrects himself, he used to be the head of navigation at NASA. He will speak about challenges that seemed impossible to overcome, and then they've been overcome. Alejandro, Miguel, San Martin.
It's this one. The floor is yours.
Grazie. Thank you very much for having me here. And so I'm going to tell you about Curiosity rover and the 7 minutes of terror. It's going to go very fast. It's a short presentation. I'm going to have a couple of presentations more in the tomorrow and on Saturday. So I always like to start by explaining why actually we'd like to explore Mars. We explore Mars for many reasons, but the main reason is we explore Mars because we want to know if there was life on Mars in the distant past, or even there is life today. And why do you think that there might have been life on Mars? Today, Mars is a dry and cold planet, not very hospitable for life, but scientists believe that 3.5 billion years ago, Mars was a planet much more like Earth, humid, and wet and warm. And as you can see in that picture, taken from a spacecraft from orbit, you can see a dry river and a delta. That indicates that Mars had actually large quantities of water. So that was a hypothesis. So we go to Mars because we want to understand if there is life. And we are interested in knowing if there is life on Mars, because as of today, the only place we know for sure that there was life is our own planet Earth. So for that, we need a big rover. I mean, the Curiosity that landed in 2012 was the largest rover that landed on Mars to test this hypothesis of life. It represented a large increase in the number of scientific instruments. We went from 10 kilograms in Spirit and Opportunity rovers to 75 kilograms. That required a very large rover, the size of a Mini Cooper. As you can see, almost 950 kilograms worth of rover to land on Mars, which represented a huge technical challenge. In the beginning, we didn't know how to do it. And you can see here the whole family of rover that we've been landing since 1997, starting with a Mars Pathfinder to the left, and Spirit and Opportunity, and then finally a big jump to Curiosity. And as I said before, this representing quite a challenge for us. So not only we had a bigger rover, but actually we wanted to land that rover in places of great scientific interest. So the scientists picked this crater, Gale crater. It's 150 kilometers wide diameter, and it has a mountain in the center. That mountain is made out of layers of minerals that were formed in the presence of water. So they might contain the secrets of the past of Mars and perhaps evidence of life. The only problem is that they didn't leave much room to land. You can see that there is only a flat surface that is safe for landing between the mountain and the rim of the crater. We call it landing between a rock and a hard place. And when you compare, here's the same picture of the crater, of Gale crater, with the different landing zones of all the previous missions. And you can see that none of the previous missions could actually go explore this crater because the landing areas, the precision of our landing system was very poor. So we had to make improvements, successive improvements until, again, we had to do a big jump in the improvement of the precision of Curiosity to actually go visit these very interesting scientific places on Mars. This is a little bit of the description of what we call the 7 minutes of terror, which is the process of landing on Mars. We arrived to the upper layers of the atmosphere at 20,000 kilometers an hour, and in 7 minutes, we need to be on the surface of Mars at 0 velocity and in one piece. Multiple pieces is easier, but the issue is to land safely on Mars. So we do that through 3 phases of slowing down or deceleration phases. The first one is the atmospheric entry. The vehicle slows down. There is an atmosphere on Mars, so we can use the atmosphere to slow, with the friction to slow down the vehicle. And from that first phase, the vehicle heats up as it exchanges kinetic energy with heat, and then release 99% of the energy that we come in with. And then we open a parachute at supersonic speed, and then since the Mars density is so low, we need a third stage of slowing down, which is the propulsive state, which is the last one. And that finally the velocities are very small to land. So why do we call it 7 minutes of terror? Well, this whole sequence happens autonomously, so we don't have any control of it. But what's even worse, the first time we actually do it is on Mars. On Earth, we test little pieces here and there, and then we have a big simulation program. We call it a Monte Carlo simulation because it's statistical in nature, where we make the system land multiple times in a computer simulation, not in real. So we are always wondering whether there is a little piece of physics that we didn't get right, okay? The 99.9% being right is not enough. It's that 1/10% is enough to kill the whole mission. So that's why during this time we call it 7 minutes of terror, because we, in those 7 minutes, are at play 8 hours of our lives and sacrifice of all our family, and let's not forget, $2.5 billion. And then, so I'm gonna go very fast through each one of these phases. So the first phase is the entry phase. We have a capsule that protects the spacecraft as it enters the atmosphere and it slows down. The bigger, the better. This is the biggest we could do that we can enter through our different facilities within the laboratory where I work. And it's a 4.5 meter diameter. Once again, we have the comparison against the Mini Cooper, so then you can see the size of this capsule. This is the largest one of a robotic spacecraft that we ever had. And of course, we need a heat shield that actually protects the spacecraft from the heat that is being generated, and also a material that is light enough, because actually we want to carry instruments to Mars. So how do we achieve that improvement in landing accuracy as respect to other missions? Well, the missions to the left, the ballistic entry, that's what we use in all the previous missions. In that system, the spacecraft center of mass is balanced, so the vehicle just enters with 0 angle of attack. And as a consequence, the only thing you can do is like when you throw a rock. If you want to hit something, you need to aim, and the moment that rock leaves your hand, you just fall through the, following the laws of gravity and friction with the air, so there's no correction you can do. However, if you actually move the center of mass of the spacecraft in a way that the spacecraft balance comes in at an angle, so essentially that's called an angle of attack, and that creates a lift force, and you can see that little force on top. And now we can control the spacecraft orientation with thrusters in a way that we can fly the spacecraft, or actually the spacecraft flies itself using an algorithm from the Apollo program that we resurrected, works very well. And so now the spacecraft actually has the knowledge of where it is, and with that little force, it's enough to actually fly its way to destination. So we use that, and you can see the little ellipse size there is the Curiosity ellipse size, and we ended up landing within 2 kilometers of the center of the ellipse. So we were very happy the first time we attempted this technology, and it worked. A lot of people felt that we were kind of crazy to not only use this technology, but use it in such a dangerous place, because had we been wrong, we would have failed. But that's what you need to do. You need to take risks in life sometimes. So the next one is the parachute phase. It's the largest supersonic at that point parachute, and you can see people there to get some scale. Parachutes, they look like simple devices, but you can see the dynamics of these parachutes as they open up, and they are pretty random, very chaotic process. And all of these things that you're seeing right now on Mars, this is obviously a slow camera, takes less than, it's 0.3 seconds, less than a second to open up. So it's a violent event, and it's very difficult to model, and many times these parachutes break in the process. So we are very, very scared. In the 7 minutes of terror, this is the peak for many of us, hoping that that parachute will open. Otherwise, it will be over pretty soon. So finally, the third phase is the propulsive phase. And we need thrusters for that, some level of thrusters. And again, I mean, here we needed to innovate because all the previous ways that we have used to land the previous rovers did not work for a rover of that size. So we tried airbags, we tried legs, we tried all sorts of things until we came out with this idea of the SkyCrane. Essentially land the rover on its wheels using not a helicopter, but not propellers, but it's actually rockets. And so we proposed this idea. I guess it's kind of a hack, so it's kind of proper for this event. And it's interesting that the lab, when we proposed this, half of the lab thought that we were brilliant, and the other half thought that we were idiots. So we knew that we were doing something right. And in any case, we did few tests, only the mechanical part. Okay, this is all the type of tests that we did. The rest was actually done in the real landing that August 5th of 2012. Also, we did some tests of the touchdown to make sure that the rover could handle those types of loads at touchdown. Those are the velocities of landing. And then here are some pictures of the rover as being assembled. That's all those circles there are the antennas for the radar. We need a very precise radar to measure the velocity and actually be able to land softly on Mars. And that's the capsule in its entirety. And these are, again, you can see the size of the rover by comparing with the technicians there assembling and testing the rover. That's a robotic arm that I wish I had time to explain it, but it's very complicated, sorts of tools, including drills to take samples of the rover and then analyze it with its analytical instruments. More instruments, more pictures. That's me taking a little nap. And then this is landing day. And this is actual video that we took, that the spacecraft took. You can see the heat shield. The spacecraft is right now on the parachute, oscillating, waiting for the right conditions to start the propulsive part of and final slowing down process. I will tell you the moment that it starts the propulsive maneuver where it gets rid of the parachute and then it lands. There, it's separated from the parachute. It doesn't maneuver to turn away from the parachute, so the parachute doesn't land on top of the spacecraft. Now it's going to get itself straight down like an elevator right now. And now it's going to go straight down, big dust. At the bottom right, you're going to see the wheel coming out, deploy before we land. And it landed that way. That was the first picture that he took. You can see Curiosity with its shadow on the... Thank you, thank you. It was a very happy moment for all of us. And we also commanded a spacecraft that is on orbit about Mars to take a picture in the right direction at the right time to see whether we can catch it. Curiosity landing, and we actually did. You can see the detail of the parachute. It's beautifully the way it's seen. This were the first moves of the first track of Curiosity as it got away from the landing side. You can see what the thrusters did there. And then this is the first selfie on Mars. And this is Mount Sharp. And now I'm going to leave you very quickly with this is the real place where we wanted to analyze with this Mount Sharp, with all the layers of clay minerals, where might hide all the secrets of the geology and astrobiology of Mars. And I leave you very quickly now with the way that it was celebrated or witnessed the landing of Curiosity around many places in the United States.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Speed chill has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for backshell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for SkyCrane. SkyCrane has started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
Thumbnails.
Right, thank you. And that ends my presentation. Thank you.
Thank you, Miguel. And you were there. And you were there.
It was fun. Yes.
Thank you.
Thank you.